So the next section in the note says more examples of functions and using this function notation. So that's f of x thing is function notation. So when you say the word using function notation, we say try to get used to this notation here. And so as practice, let's work out each of these quantities. So A says, what is the value of function 1? So that's saying, what is the y value when x is equal to 1? And so function 1 is, everywhere I see x, I put in the value 1. So it's 1 cubed plus 1 plus 1. So it's 1 plus 1 plus 1, so function 1 is 3. Yay, we like that, we can do that. Likewise, function minus 3, again, everywhere you see x, you substitute minus 3. So I get minus 3 cubed plus minus 3 plus 1. So minus 3 cubed is minus 27. Minus 27 minus 3 is minus 30. Add 1, minus 29. That's function minus 3 when the function is x cubed plus x plus 1. So in this case, in both cases, you can see function 1, it's a number. Function minus 3, it's a number in there. Part C says, instead of having a specific number, let's have a general number called t. So everywhere I see x, I have to substitute t. And so I have t cubed plus t plus 1. And of course that looks awfully like x cubed plus x plus 1. And what it's saying in here is when you use this function notation, the actual name of the variable doesn't matter. It will represent the same set of ordered pairs, whether I have a t, an x, a y, or whatever in there. We tend to use x just because we lack imagination. Okay? But you can use any letter you like. Later on, we'll see things like this are useful. What is function 2a? Well, everywhere I see x, I have to substitute 2a. So function 2a will be 2a cubed plus 2a plus 1. 2a cubed is 8a cubed, so I have 8a cubed plus 2a plus 1. And so there is a formula in terms of a for function 2a. What use is that? Well, I'll wait till we get to calculus and show you some uses of that. Likewise, function x plus 1, and this looks slightly confusing because we've got x's there, but the notation says, wherever you see x, substitute x plus 1. So this becomes x plus 1 all cubed plus x plus 1 plus 1. That number, x plus 1, is exactly what I did up here, where I saw minus 3. I just substituted it in. Now, in this case, I can do some algebra on that, and I can expand that out. And I will get x cubed plus 3x squared plus 3x plus 1 plus x plus 1 plus 1. So if I now collect like terms, I will have x cubed plus 3x squared plus 4x plus 3. And so function x plus 1 is this number here. X cubed plus 3x squared plus 4x plus 3. The important point about all of this is not can you do the algebra, but can you understand what that notation is actually referring to. And as I say, it seems a bit of a mystery as why I would even want to do that. But we will see applications of that coming up. Another example, if function x is 3x minus 6, what's function 1 and function minus 2? That one we can do. Function 1 is 3 times 1 minus 6, so I get minus 3. Function minus 2 is 3 times minus 2 minus 6, so I get minus 12. That I think we can do. The next one says, for what values of a does a equal function a? So in fact, we've got an equation there. So that is an equation that we need to solve. So it says, for what values of a does a equal function a? Well, function a is 3 times a minus 6. So this is a linear equation in one variable. To solve it, I just make a the subject. So I have 2a is equal to 6, and so a is equal to 3. That's the value of a that makes a equal to function a. Again, it's not immediately obvious why I want to know that, but you'll see we use this sort of thing a lot, come calculus. Let me put a geometric interpretation on that. Okay, so first of all, let me draw the graph of the function. So this is the graph here of function x is equal to 3x minus 6. It goes something like that. So it's got an x-intercept of 2 and a y-intercept of minus 6 down there. So that's the graph of y is equal to 3x minus 6. So for a particular value of x, that gives me the value of function x, if you like. Because y and function x, they're the same thing. Now, my equation over here said, when is that value the same as the value of x itself? So if I were to draw the graph of y is equal to x, if I were to draw the graph of y equal to x in here, so when the x and y values are the same, and that is a straight line through the origin of slope 1. And if I get this right, I'll do this. Whoops. So there's the graph of y is equal to x. This point here is the point where x is equal to function x. The x value is the same as the y value, in fact, in there. So what I've managed to do in this case is I've found where x is equal to function x. That's actually the solution to a set of simultaneous equations sitting in there. So that says x is equal to 3 is the solution sitting in there. And you can see that therefore y, or function x, is also equal to 3. So that's a geometric interpretation of what we did there in B. And it also allows us to do part C geometrically as well, but let's do it algebraically first. Part C says, for what values of x is function x greater than x? So function x is 3x minus 6 is greater than x. So if I solve that, bring that over, that's 2x is greater than 6. So that says when x is greater than 3. They're the values of x where function x is greater than x. And if we look on our graph, I can think of that. This is saying, where is the graph of the function? Where is that number bigger than the graph of y is equal to x? So for example, if I'm here, here's the graph of y is equal to x, here the graph of function x is above it. So the set of x values where the graph of function x is above the graph of y equal to x is these values of x out here. Alternatively, you can think of it for these points out here, that value, the value of function x, is greater than the x value. That's another way of thinking of it. But I'll leave it there. Another function, in this case a quadratic function, and it says find f of 3, so that much is straightforward in that everywhere where I see x, I substitute 3. Likewise, when I evaluate function minus 2, everywhere I see x, I put minus 2, and so function minus 2 will be 3. Part B says find function A. That I can do because everywhere I see x, I just substitute A. Then it says find function B. Everywhere where I see x, I substitute B. So function A is A squared minus 1, function B is B squared minus 1. Then it says find function A plus B. So what this is saying is start with the value A, add to it the value of B, then work out what the function of that quantity is. So function A plus B is, everywhere I see x, I have to put A plus B. So I get A plus B squared minus 1. And if I were to expand that out, I would have A squared plus 2AB plus B squared minus 1. Importantly in this case, notice that if I went function A plus function B, that would be A squared plus B squared minus 2. Definitely not that. So note, function A plus function B is not the same as function A plus B. This one says if you have two numbers, add them up and then work out the function associated with that, the function value. You don't get the same as working out the function value associated with A, working out the function value associated with B and adding those. They are definitely different numbers. And that has importance when we do algebra with these things. And the last part says determine the range of f. Well, I think the easiest way to determine the range is actually to sketch the graph. And this is a parabola. It's concave up. It has a y-intercept of -1. And in fact, it has a vertex of 0, -1. And x-intercepts are +1 and -1. So the graph, whoops, it goes through 4, go through there and there. So it'll look something like this. My parabolas aren't so crash hot, but it will look like that. That will be the graph of y is equal to x squared minus 1. It's supposed to pass through -1 and +1. And so the range is the set of y values for which there's a point associated with it. And if I draw my horizontal line here, you can see I have a y value of -1 and every other y value possible up there. So the range, so part C, I'll put it here, the range will be the set of y values such that y is greater than or equal to -1. This example is a rather strange one, but it was in the notes, so I thought I'd better go through it. So it says, if we know that function a plus 2 is a plus 5, what is function x? And so in here what you do is, there I actually want that to be x, so I let a plus 2 be x, which means that a is x minus 2. And therefore, from this equation, function a plus 2, which is x, is equal to x minus 2 plus 5. A is x minus 2. And that becomes x plus 3. So if function a plus 2 is a plus 5, then function x was in fact x plus 3. So that's just an exercise in algebraic manipulation. Likewise, in part B, it says, if function 2a is this, what is function x? So I begin by letting 2a be equal to x. So let 2a be equal to x, and that says, therefore, a is x on 2. And so from the equation, function 2a is 4a squared minus 4a plus 1, I have function x is 4 times, now a is x on 2, so I have x on 2 squared minus 4 lots of x on 2 plus 1. And I can simplify that a little bit because x on 2 all squared is x squared on 4. 4 times x squared on 4 is just x squared. Minus 4 times x on 2 is minus 2x plus 1. And so there's my formula for function x. So all of these examples are just trying to get you used to the idea of the function notation. And the last concept that I want to talk about today, and I guess I should reiterate where I am. Here we're just looking at examples of functions and practicing using function notation. So the kind of example that I want to talk about here is in fact a piecewise function. A piecewise function is a function that has different rules on different parts of the domain. And they're quite often written like this. So it says, in fact I might even draw the picture here. It says, look, between minus 2 and 3. So if I'm here between, and they're open circles, so between minus 2 and 3, the function is just 0. So if I were to draw the graph, it would just be the line y is equal to 0. It would look like that. That's y is equal to 0. From 3 to 5, between 3 and 5, and again it's an open circle there, it looks like y is equal to x. And so that graph will be up here. 3, there, and whoops, went too far. There it is, just a 5, and 3 was included, so that's actually coloured in, that one. Notice in here, so this is y is equal to x. So on this part of the domain, the rule is y is equal to 0. On this part of the domain, the rule is y is equal to x. The important notice here, I should say, at x equal to 3, for this to be a function, there can only be one value associated with each value of x that's used. So when x is equal to 3, we don't use that one, we use the coloured in circle. If they had both been coloured in, then this wouldn't be the graph of a function, because there would be two values for f at x equal to 3. Okay, but since there's only one value associated with that, that's a function. So it says, find the domain. Well, for what values of x is this rule applied? And the answer is it goes from minus 2 up to 5. For every value of x in there, we've got an associated value for y. So the domain is the set of x values between minus 2 and 5. In that case, they're the values for x in this particular rule. The associated values for y, the range, will be in here just 0, and plus, or union, to use the set notation that we introduced earlier, these values here between 3 and this one here will go up to 5. So it's the set of y values between 3 and 5. That's our range in that case. The values for y for which there is a x value associated with it, 0, and then those values of y here. And another piecewise function. This one says between minus 2 and 0, the rule is x minus 1. So between minus 2 and 0, here. So x minus 1 is down here. So minus 2 minus 1 is minus 3. So that point is on it. Minus 1 is coloured in. So there it is. So on that part of the domain, there's the graph. Y is equal to x minus 1. Between 0 and 1, there's nothing defined. We then go from 1 to 2, and this here, if I go y is equal to 2x minus x squared, that's the same as x 2 minus x. So, this is a quadratic, so the graph is a parabola. It's concave down. It's concave down, and it has x-intercepts at 0 and 2. So, has an x-intercept here and an x-intercept here. And when x is equal to 1, it's equal to 2. So it actually does this. So I'm going to dot this in just for the minute. This is the graph. Right, that's the graph of the parabola associated with 2x minus x squared. However, it only applies, in this case, for x between 1 and 2. So this is, in fact, the bit, so that's an open circle. That's the bit that we're actually using, just that part there. So that's y is equal to 2x minus x squared. So for this particular function, its domain is those x values between minus 2 and 0, and those x values between 1 and 2. So the domain is the set of x values between minus 2, I keep putting the equals in there, that's just less than, x less than equal to 0, union with the set of x values between 1 and 2. All of those values plus all of those values is how we interpret that writing. The associated values for y will be all these y values here between minus 3 and minus 1. Union with these y values here between 0 and 1. So we've got 0 is less than y is less than or equal to 1.